All right, so for problems 15 and 16, Eileen has 7 homework assignments to complete. She wants to do 2 of them on Thursday and the other 5 on Saturday. And question 15 is only addressing in how many ways can she order Thursday's work. Now remember, Thursday we are doing 2 homework assignments. How many does she have total? She has 7 homework assignments total to complete. So important stuff is there are, and my pen's not working, it should be, there are 7, I'm getting frustrated with the pen situation. There are 7 homework assignments to complete, and she wants to do 2 of these on Thursday. All right, now when you're trying to figure out a method to do counting problems, there are at least 2 questions you should ask yourself. Can you reuse values? If the answer is no, then that means you can use a permutation or a combination. If the answer is yes, you have to use the fundamental counting principle and just multiply. Can we reuse our homework assignments? No, you can redo homework assignments, but when you're selecting 2 to do Thursday, when you pick the first one, you don't want to pick the first one again, right? So definitely no, we're not reusing the homework assignments when we're making our selections. Therefore, a permutation or a combination does apply in this case. The next question you should ask yourself then is, does order matter? Does order matter in selecting the homeworks? You know what? It doesn't say clearly that order does or does not matter in this case. And I don't know, I think there's an opinion here. It needs to be made clear, because if you're selecting 2 homework assignments to do on Thursday, the order that you do them in might not matter to you. But when they ask this question, they do intend order to matter. So if you do math first and then history, that is a different possibility than doing history first and then math. So does order matter? Yes, they intend it to matter. I think if I were to put this question on a test, I would want to say more specifically that order does matter. That if you do math and history, that is a separate possibility than doing history than math. And you could tell it, I mean, it really is kind of a separate possibility, right? But if you're just grabbing 2 subjects to do, order might not matter to you. So it's something to think about. But after all that, if order does matter, then you would need to use a permutation. If order did not matter, kind of like just creating a committee, then a combination would work. So how do we do this? Well, we have a permutation. How many do we have to choose from? 7. How many are we choosing? 2, because Thursday we're just doing 2 assignments. So the formula for that is 7 factorial divided by the difference, 7 minus 2 factorial, which would give you 7 factorial in the numerator, 5 in the denominator. Remember, we talked about the quick way to do this is just to write the top down until you get to the bottom, but don't include the 5. So that's just 7 times 6, which is 42. Again, remember, just real quick to show you the long way, that's 7 times 6 times 5 factorial divided by 5 factorial, and the 5 factorials cancel. So you can always write the top one down, and you include the numbers until you get to that number, and you don't include the 5. So it'd be 7 times 6. Don't include the 5 times 4 times 3 times 2 times 1 because it canceled out. Now for problem 16, we're assuming still Eileen has 7 assignments. She needs to complete 2 on Thursday and 5 on Saturday. So this is saying, assuming she finishes Thursday's work successfully, and how many ways can she order Saturday's work? So we've already decided that we're not reusing, which a permutation and combination applies, and that when you're creating an assignment list, the order you do it in does matter. So we're talking about a permutation in this case. So we have a permutation. All right. And earlier we did 7 choose 2 because on Thursday she has 2. So why not 7 choose 5? Well, we've already done Thursday's work, right? So we don't have 7 assignments anymore. We only have 5 assignments to choose from, and we've got to do all 5 of them on Saturday. So this is the permutation of 5 choose 5. If I use that formula, that's 5 factorial divided by 5 minus 5 factorial, which is 5 factorial over 0 factorial. We know 0 factorial is 1. So essentially, it's just 5 times 4 times 3 times 2 times 1. And that gives us, let me get my calculator and I'll tell you, 120 possibilities. And again, my zeros are always looking a little bit 6-ish. There we go. 120 possibilities for 5 choose 5. And we're doing all 5 of them. So really that's just arranging or reordering the assignments. Now for 17 through 21, we have 10 players on a basketball team. We want to find the number of choices the coach has in selecting each of the following. So if we need 4 players to carry the team equipment, so things we need to think about, again, can we reuse? If the answer is yes, we can reuse, then we can't use a permutation or combination. If the answer is no, then we can either use a permutation or a combination depending on what applies. Do you want to reuse your players? Well, no. You can't have players playing the same one player playing 2 different positions. So when you use a player for some kind of position, then he's used up or she's used up. So no, we are not reusing, which means a permutation or a combination would apply. Once you get to that point, you need to know if order matters. Well, if we're picking people to carry team equipment, the order we pick those in really doesn't matter, right? A group is a group. This is like picking a subcommittee. So we're going to do a combination because order does not matter on a combination. Remember the trick to remember that? A combination lock is not a combination at all. Okay? It might be a permutation, or if you can reuse the numbers on the combination lock, it's neither a permutation nor a combination, but it's definitely not a combination. So anyway, we're going to use a combination here because order does not matter. And we have 10 players on the team, so that's how many we have to choose from, and 4 players to carry the equipment. We're going to pick 4 of them. Now the formula there is the 10 goes on top. How many you have to choose from always goes on top. Now we're going to divide by the 4 factorial because that gets rid of duplicates, and then just like in a permutation, you have 10 minus 4 factorial. So now we have 10 factorial divided by 4 factorial times 6 factorial. Again, you cannot multiply the 4 factorial times the 6 factorial and get 24 factorial. That's not correct. What you want to do is write the top one down to match the bottom one. Don't include the 6. So this is 10 times 9 times 8 times 7. The 6 factorials will cancel, and that's divided by 4 times 3 times 2 times 1. If you really wanted to avoid some extra calculations, this 4 times 2 will cancel with that 8, or just type it all in your calculator. Now when I do that, I'm going to leave you live. 10 times 9 times 7, and the numerator is 630, divided by 3 times 1, 3 in the denominator, and 630 divided by 3 is 210. So there are 210 different ways to select 4 people from 10 people to carry equipment. Now for number 18, we still have 10 players, okay? We want to find 2 players for guard position, and 2 players for forward positions. Now notice the and. That is a clear multiplication, okay? So in our first task, we're going to pick the guard positions. And our second task over here, we're going to multiply because of the and we're going to pick forward positions. Now we already know we're not going to reuse people, right? We're not going to reuse the 10 players. You can't have a player that's going to play guard and forward, or both guard positions. That's impossible. So we're not reusing, which means a permutation or combination applies. But you know what? The order doesn't matter here. If you pick, Kathy and Suzanne for your guard positions, that's no different than picking Suzanne and then Kathy. You with me? Therefore, the order doesn't matter. We need to use combinations. And again, a combination can be used when you're not reusing and order does not matter. All right, so I'm going to have a combination up here, so I need a combination. From the guard position, how many people do we have to pick from? 10, and we're picking 2 of them. For the forward position, we have 10 people to pick from, right? Wrong, right? We've already picked 2 of them to play guard, so now there's only 8 people left to choose from. And how many are we picking for 2 forward positions? So we're going to pick 2. So this is the calculations we have to do. We have to calculate a combination of 10 choose 2, and then a combination of 8 choose 2, and then we're going to multiply those 2 values together using the multiplication principle. So I have, for 10 choose 2, I have 10 factorial divided by 2 factorial, and then remember you subtract them. So that's 10 minus 2 factorial. Continue down here to simplify. That's 10 factorial divided by 2 factorial times 8 factorial. Remember the rule is you write the top down to match the biggest one on the bottom. So that's 10 times 9. The 8 factorials will cancel, and then I have 2 times 1 here. And we'll calculate that in just a minute. But in, let's use green, I'm going to calculate 8 choose 2. So that's going to be 8 factorial divided by 2 factorial, and then also divided by 8 minus 2 factorial. So this is 8 factorial over 2 factorial times 6 factorial. That denominator is not 12 factorial. Again, you can't do that. But I can write the bigger one down to match the smaller one. So it's 8 times 7. The 6 factorials cancel. And then you still have a 2 factorial on the bottom, which is 2 times 1. Now when I simplify that, so that's going to equal, remember, in the end I'm multiplying these 2 answers together. So I can divide 2 into this 10 right here. That leaves me with 5 times 9 is 45 divided by 1, which is 45. And then 2 goes into 8 4 times, and 4 times 7 is 28. Then finally 45 times 28 is going to give me, when I locate my calculator, here we go, 45 times 28, and I get 1,260 possibilities for selecting 2 guards and 2 forwards to play our game. Okay, so we still have 10 players on the basketball team. We want to find the number of choices the coach has in selecting 5 starters and 5 subs. We got 10 people. That uses everybody up, right? We've decided that the order does not matter. To pick the 5 starters and the 5 subs, you got to be careful. You know, if you were assigning positions, picking those 5 starters, the order would matter. Because if you pick, again, Kathy to be a starter and she's guard, and then Suzanne to be a starter and she's a forward, that would be different than flipping that around. But this is just picking 5 starters, period, not positions at all. So if I pick 5 starters, then I have a combination of, I have 10 people to pick from, and I'm picking 5 of them. But I'm also, and means multiply, I'm picking 5 subs. Now, y'all have already picked 5 starters, so I've got 5 people left over to choose from, and I'm picking all 5 of them. And there's really only one way to do that. You're going to see that in a minute. You just, all 5 of them are going to be subs, right? Let's do this calculation. Combination of 10 choose 5 is 10 factorial divided by 5 factorial, and then divided by 10 minus 5 factorial. If I continue down, simplifying, that's 10 factorial divided by 5 factorial times 5 factorial. I write the top one down to match the bigger one in the bottom. Well, 5 and 5 is the same size, so it doesn't matter which one you cancel, but one of them will cancel. 10 times 9 times 8 times 7 times 6. I don't write the 5s because they cancel. And in the denominator, I still have this 5 factorial, 5 times 4 times 3 times 2 times 1. If you wanted to cancel some things beforehand, this 10 would cancel with this 5 times 2. You could even do other things like 3 goes into 9, but I don't know if I want to go that far with it. I'm just going to type that in my calculator. It's 9 times 8 times 7 times 6. And that's 3,024 divided by the denominator, which is 4 times 3 times 1, which is 12. So overall, I have 252 ways just to pick a combination of 10 choose 5. Now, switching colors on you, let's do a combination of 5 choose 5. Remember, that's 5 factorial over 5 factorial times 5 minus 5 factorial. Well, let's think about this. That's just 0 factorial, which is 1, so this is gone. 5 factorial over 5 factorial is 1. Now I multiply these values together. 252 times 1 gives me a final answer of 252 ways to pick 5 starters, and then the rest of them will be subs. So really the second calculation you didn't have to do, but just to make things clear, we might as well. And next we still have the 10 players. They want us to pick 2 groups of 4. Didn't say that order matters, so we're going to assume it does not matter. You're picking just a group, right? Usually for a group, order doesn't matter. So we have a combination of 10, choose 4. Now, remember, we've already picked these people. So times, because it's 2 groups, this group and this group, we need to multiply a combination of, now left over I have 6 people to pick 4. But now here's an extra problem here, an extra issue that we didn't have to deal with on the last situation, because when we did 10 choose 5 and number 19 to pick our 5 starters, we didn't have to worry about repetition. So here's the problem though. When you pick a group of 4 people, and then over here you pick a group of 4 people, there may be repetition within this group and this group. So we're going to have to divide by the possibilities of the repetition. Does that make sense? Because in this group, it could be Aaron, Bill, Carly, and Deborah. And in this group, you could also have Aaron, Bill, Carly, and Deborah. And since that can happen because of these 2 groups, we're going to divide by, what happened to my pen? We're going to divide by 2 factorial. So here we go. 10 choose 4. I'm going to do this in green. This is 10 factorial divided by 4 factorial times 10 minus 4 factorial, which is 6 factorial. And then I'm going to do this one in red. So we're going to multiply that by 6 factorial divided by 4 factorial, and then subtract 6 minus 4 factorial. And then all of that is divided by 2 factorial. Okay. Now, if I continue on with the process of simplifying, then I have 10 factorial divided by 4 factorial times 10 minus 4, which is 6 factorial, and then times, I have 6 factorial over 4 factorial times 2 factorial, and that's all still divided by 2 factorial. I keep going with my simplifying. Now I have 10 factorial, and I'm going to write it all the way down. Actually, let me back up. I'm going to write it all the way down until it matches the biggest one in the denominator. So the 10 I'm going to write down till I get to 6, but I'm not going to write the 6. So it's 10 times 9 times 8 times 7. The 6 factorials cancel, but this 4 factorial is still there. 4 times 3 times 2 times 1. Now I'm going to do the same thing with my 6 factorial. I'm going to write it down to 4. So 6 times 5, the 4 factorials cancel. And then still divided by 2 times 1. And then in the denominator, I still have 2 times 1. Continue the simplifying. In green, I have 10 times 9 times 8 times 7 divided by, and I'm searching for my calculator, 4 times 3 times 2 times 1. If you wanted to do a little extra and cancel 4 times 2 is 8, you can, or you can just type right in. So 10 times 9 times 7, and then that's divided by 3, and I get 210 for my combination of 10 choose 4. Now for my combination of 6 choose 4, I have 30 on top divided by 2, that's 15. And then, of course, that's divided by 2 times 1, which is 2. And my final answer is 210 times 15. And that's divided by 2. And again, an answer of 1,575. But the trigger on that one is these duplicates, because these groups are interchangeable. So it's a possibility of having double the amount of groups represented. And again, I gave you that list of an example of it could be in this group or it can be in this group, and we don't want to count them twice. Now for this problem, it asks for a group of 3 or more players. So a group of 3 or more players would be 3 players. Again, pen issues. 3 players. You could have 4 players, 5 players, 6 players, 7 players, 8 players, 9 players, 10 players. You would have to calculate all of those separately. So that would be 10 choose 3, 10 choose 4, 10 choose 5, 10 choose 6, and there's an or, so you would add all those together. I'm thinking that the complement would be a little bit easier, and the complement would be how many do you have total in terms of subsets of players? So how many subsets are there? So that's what we're going to find first, and then we're going to subtract out not this. So not more than 3. Well, what is not more than 3? Well, that means 0 players, 1 player, 2 players, not 3 players, right? So not more than 3 is 0, 1, or 2. So the big plan is to take the total number of subsets and subtract out 0 player or 1 player or 2 players. Think we can do that? Okay, now how about the total number of subsets? Well, to find the total number of subsets of just a set is always 2 raised to the number of items you have, which is 10 players in this case. So 2 to the 10th minus, now, here 0 players would be a combination of 10 choose 0. Plus 1 player would be a combination of 10 choose 1. Plus 2 players would be a combination of 10 choose 2. Now, why are we adding this and not multiplying these together? Because we're not saying we have a group of 10 choose 0 and a group of 10 choose 1 and a group of 10 choose 2. This is an or situation. You have 0 players or 1 player or 2 players. That's really important. We have to keep up with that. All right, now let's do our calculations. 2 to the 10th is 1024. So we have 1024. Again, that's a 0, not a 6. There we go. Minus, now let's do some calculations. 10 choose 0. How many ways can we do that? Let's just calculate it. You want to? That's 10 factorial over 0 factorial times 10 minus 10 factorial. Or 10 minus, my bad, 0 factorial. Now when you simplify that, that's 10 factorial. We know 0 factorial is 1, so I'm not going to write it. Over 10 factorial. Y'all, that's just 1. All right? Now let's do 10 choose 1. So I have 10 factorial over 1 factorial times 10 minus 1 factorial. If I keep going here underneath, that's 10 factorial over 1 factorial times 9 factorial. Well, if I write the top one down to match the bottom one, all I'm going to have left is 10. That's just equal to 10. So now I have 1 plus 10 plus, now I'm going to do 10 choose 2. So that's 10 factorial over 2 factorial. And that's 10 minus 2 factorial. If I come down below, that's 10 times 9. It cancels with that 8 factorial divided by 2 times 1. Now 10 times 9 is 90, divided by 2 is 45. So basically, I have 1024 minus 1 plus 10 plus 45. I'm going to switch colors on you. So that's 1024 minus, sum this up again, 1 plus 10 plus 45. That's 1024 minus 1 plus 10 is 11. 11 plus 45. I've got some neatness issues. There we go. 1 plus 10 plus 45 is 11 plus 45 is going to be 56. And 1024 minus 56 gives me 968 possibilities for having 3 players, or 4 players, or 5 players, or 6 players, or 7 players, and get it, or 8 players, which is a group of 3 or more players. Now for problems 22 through 27, we've got some on-off switches. So it says determine the number of possible settings for a row of 5 on-off switches under each condition. The first condition, there are no restrictions. So, hey, we got 5 on-off switches, right? So the first one can be on or off, the second one can be on or off, the third one can be on or off, the fourth one can be on or off, and the fifth one could be on or off. Now, one thing we have to decide, can we reuse? In other words, if we select on, can we select on again? Yeah, we sure can. So what that means is we can't use a combination or a permutation in this situation at all, because we can reuse those outcomes. So the first position, this is just the first switch, second switch, third switch, fourth switch, and the fifth switch. The first one can be on or off. That's 2 possibilities. The second one can be on or off. Also 2 possibilities. Third one on or off. Fourth one on or off. Fifth one on or off. That's 2 to the 5th power, which gives you a final result of 32 possible outcomes for a group of 5 switches to be on or off. Now for the next example, same 5 switches, not working, 1, 2, 3, 4, 5. Now it says the first and the fifth switches must be on. Okay, that's fine. The first one must be on, and the fifth one, this is the fifth one, must be on. So, for the first position, I only got 1 possibility, it must be on. For the fifth position, I only have 1 possibility, it must be on. But the second switch, it can be off or on, so that's 2. The third switch can be on or off, and the fourth switch can be on or off. And since we have to make all of these decisions, this is multiplication. It's not this switch or this switch or this switch. It's this switch and this switch and this switch. You see what I'm saying? So this is a multiplication problem. 1 times 2 times 2 times 2 times 1 is equal to 8. So there are 8 possibilities for the switches, with the extra condition that the first one and the fifth one must be on. For question 24, we still have 5 rows of switches. I'm just doing them in order, so this is the first switch, this is the fifth switch. Okay, the first and the fifth switches must be the same. Okay, so let's think about it. The first and the fifth must be the same. If the first one can be on or off, though, we have 2 options. The second one can be on or off. The third one can be on or off. The fourth one can be on or off. The fifth one just has to match whatever this one is. So there's really only 1 possibility. It may be on if this one was on, or it may be off if that one was off, but only 1 option, and it's whatever the first one's on. So if we multiply those together, 2 times 2 is 4 times 2 is 8 times 2 is 16, we get 16 possible outcomes for the first and the fifth switches must be the same. Now for problem 25, it says no 2 adjacent switches can be off. So for considering our 5 options, okay, and this is the first switch, then we have 2 possibilities for the first switch. For the second switch, let's think about this. Now normally we have 2 possibilities, but it says no 2 adjacent switches can both be off. So if this, for our first switch, if we selected on, then we would have 2 possibilities. But if we selected off, then we would only have 1 possibility, because right next door can't be off also. Hey, we can't do it this way. It's not uniform. So no 2 adjacent switches next to each other can be off or on. You may want to do a tree diagram for this. Okay, so instead of using the multiplication principle, which we cannot, what you might want to do is just a diagram. So we have, remember, 5 switches. So the first switch could be either off or on. They said 1 represents on and 0 represents off. Okay, so no two adjacent switches can both be off. That cannot happen. So if this one is on, then for the second possibility, you could have on or off. But here, you can only have on, because I can't have two ons, two offs next to each other. Now when we branch for the second time, maybe I should change colors of our branches, then I could have on or off here, but here I can only have on. Again, no two adjacent switches can both be off. Here I have a choice of on or off. For my fourth switch, right here, I have choices of on or off, but here I only have on, so we don't have two O's right next to each other. My next situation is on or off. My next situation is on or off, but down here, I can only be turned on, so I don't have two zeros next to each other. And then the last option, right here with this on, could be on or off. Here is only on, because a 0 cannot be next to another 0. Here, I have two choices. I don't want to flip them around, on or off. Here, I have two choices, on or off. Here, I only have the one choice, flip that next one on. Here, I have on or off. But here, only on, and here I have on or off. Now, if we list these possibilities, and it's a lot, see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I see 13 possibilities. Okay, we don't have to list them, actually. It just said determine the number of possible settings. You could list them, though, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1. It's hard to remember which ones you've done. And if you were going to do this, here's my advice. If you had to list them, what would you do? Follow your pattern. 1, 1, 1, 1, 1. And we did that one, so you mark it out. And then 1, 1, 1, 1, 0. And you mark that one out. And then you get to this next one, which is 1, 1, 1, 0, 1. Mark that one out. And then 1, 1, we've already gone that path. You're done with that line. 1, 1, 0, 1, 1. Did that one. And then 1, 1, 0, 1, 0. And that's going to take me forever. But you see what I mean? If you mark them out and then you just make the path to get to the next one in line and mark it out when you've done it, you won't get yourself confused like I often do when I don't mark them. I can't remember where I left off. Now, 26, the last one of these, and the last one for this video, and I'll move to another video, part 3, to finish up the problems. But it says no two adjacent switches can be set the same. Now, again, we've got some issues, if we attempt to list our 5 switches, we might have a problem with the choice that we make before affecting the next one in line. So you may want to do a branch. Again, you can be on or off. And for the next branch, okay, now if this is on, this one has to be off. That's my only choice. If this one's off, this one has to be on. Interesting, right? My next choice for my third, if this one's off, it has to be on. If this one's on, it has to be off. You see where we're going with this? And if this was on, this one has to be off. If this one's off, this one has to be on. How many? 1, 2, 3, 4. I got one more switch. If this one's off, it has to be on. If this one's on, it has to be off. Wow, that's only 2 possibilities if we do that. Alternating, you either start with on and you alternate, or you start with off and you alternate. So this is 1, 0, 1, 0, 1 and 0, 1, 0, 1, 0. Just 2. Weird problem. All right, come back for part 3 and we'll work on problems 27 on. I didn't realize there was one more of these 22 through 27. If I would have read better, I would have seen that. But let's finish this one up before I move on to part 3 for the video. At least 2 switches must be on. Now, whenever you see this at least business, you're probably going to need a complement. So 2 switches must be on means 2 or 3 or 4 or 5. Now, we could try to calculate that, but oh my goodness, it would be so much easier to do the complement And the complement of not this is actually, let's think about it. What does it mean to be not 2 or 3 or 4 or 5? Not 2 or 3 or 4 or 5 means 0 or 1. Okay, now to do that, you have to find the total number of possibilities. So you take the total number of possibilities for your switches, which we've already calculated, and minus 0 or 0 switches on or 1 switch on. Okay, so total possibilities, remember we did this for problem, I think, 22. So you have 2 to the 5th options because you have 5 switches, and each one of those can be on or off. That's where the 2 comes from, is the on or off, and you do that 5 times, that's 2 to the 5th. Minus, now it says at least 2 switches must be on, so not at least 2 switches must be on, must be 0's on and 1 is on. You see what I mean? So 0 switches on, there's only one way to do that, y'all, is have them all off. That's the only possibility. Every one of them is off. Now, if 1 switch is on, think about your 5 possibilities. It could be this one, or this one, or this one, or this one, or this one. That's actually 5 different options where just 1 is on. If I make that more clear, maybe I should. Those 5 possibilities are 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0. Remember where 0 means it's off and the 1 means it's on. Those are the 5 possibilities right there for 1 switch is on. And if I calculate that, that's 32 minus 1 plus 5 is 6. 32 minus 6 is 26 possibilities for at least 2 switches must be on.